Hi, welcome back to Programming in Python learning series. This is session 14. In the previous sessions, we went through topics up to sorting, and in this session, we look at searching. This kind of concludes the topics for Python for CBSE 11th and 12th grade students. So, what is searching and why we use searching, right? So searching is basically what we normally do, search for something. And in the computer parlance, it's looking for a particular element from a collection of elements. Search results indicate if the intended element is present or not. If present, the location of the particular element is also found. Searching is an important technique in computer science. When we deal with huge amounts of data and I want to identify or locate a particular data element or set of data element, I need to have a way of identifying, and searching comes in handy because searching is an important technique used to deal with data. Of course, we talked about why, right? A lot of data gets processed and stored in computers. Knowing where each element is located is virtually impossible unless we have a supercomputer memory. It's not going to be possible even for computers unless you have an indexing process or a way to refer quickly. Searching is the only way to identify and locate a portion of specific data. And data need to be identified quickly for processing, and searching methods are a must. Let's look at some searching types or searching methods. First one is the linear search. Linear search is the most fundamental and simplest searching method. It's very exhaustive, and in case of large data sets, it's highly time consuming. What happens is each and every element in the target data set is compared against the element that we want to search, which is called a key. So every element in the target data set where we want to search for the key is compared, and when it is identified, it's going to return the result or consider that the search is unsuccessful. This is suitable for small data sets, as I said earlier. For large data sets, it's going to be highly time consuming and will not be very useful. Binary search. Binary search makes use of ordered list of elements to quickly search an item or key. So the most important aspect or a prerequisite for binary search to work is having an ordered set of elements, either ascending or descending, or alphabets as a sorted in the alphabetical order A to Z or Z to A, one way or other. It needs a sorted list of elements for it to work. Key to be searched is compared with the middle of the sorted list, resulting in one of the three statuses. The key element or the data item that we want to be found in the uh, target list, that element is compared against the middle of the sorted list. And if there is a match, it's going to return yes, a match found, or it will return whether the key element is greater than the compared element or lesser than the compared element, effectively cutting down the target for the next iteration or pass in half. So if it is, say, for example, the key element that we are searching is greater than the middle element in the target list, naturally the next pass or next iteration will have to deal with the second half of the list. That is enough. Or the other way around, if the key is lesser than the middle element, it's only enough to search the first half of the target list against the key value. We don't have to go to the entire list all over again. So that basically, well, for each pass, the size of the target list or the search list comes down by half. So it's much better in terms of efficiency compared to the linear search. Search by hashing is the next technique, where the presence of keys found within one pass or one step. So for that to happen, a formula called hash function is used to calculate the value at an index in the list. This takes elements in a list one by one and generates an index value for each element. What it does is So it takes an element in the target list, divides by total number of elements, and finds the remainder. It's also called remainder technique or remainder search technique. So it takes the remainder as a value and place it in that position for further processing. Let's go over each search in detail. First, linear search. As we saw, it's the most fundamental and simplest search method. It's an exhaustive searching technique. Each element of a given list is compared with the item to be searched, which is key. This process continues until an element matching the key is found or the search is considered unsuccessful. This item by item comparison is done in the order of elements present in the list, hence also called sequential search or serial search. Remember, for a linear search, the target data set is unordered, and it has to go one by one. It doesn't know whether the next element is going to be large or small, like in the binary search. So it is also called sequential search or serial search. This method is useful for small collection of items, that is unordered. Let's look at a depiction of how the linear search works. So we have a list that is a target list we want to search the key in. So I have say 9 values, and I want to identify 41, whether 41 is present in that particular target list or not. So the linear search compares each element of the target list with the key to be searched. So here k is 41, k the key is 41, and key is not 70, so it moves on to the next one. Key is not 40, it moves on to the next one. Key is not 30, I have 41 here, and so on until it finds k in the position, index position 5, meaning sixth element of the target list. Remember, indexes start from 0 and go on in ascending order, positive integers. So when we say index 5, it's the sixth physical position in that list. So k as 41 is found in the index position of 5. So just imagine we just have 9 elements here, and we are trying to find an element that is sitting in the place or fifth index position or sixth physical position of the list. Imagine we have humongous data that runs into millions of values, millions of records sometimes, and I want to find one small element. This particular search method is not going to be effective. It might take hours together depending on the size of the data. So this is good for a small data set. It can be ordered or not, it doesn't matter, but typically an ordered data set is fed to this particular search. Let's look at the basic algorithm to implement linear search in any of the programming languages. Create a function which takes arguments, the list target list, the key to be found, and the number of elements in that particular list. Set the index to be 0 for us to process through uh, the list and identify where my target or key is found. While index is less than n, repeat step 3, which means for all elements in the list, do whatever is following. If the list element at index is key, then meaning if the elements are matching, then element found at position index plus 1. Remember, this is the physical position, not the index position. Stop the process. Once it is found, stop the process. Else, set index equal to index plus, move on to the right one or next index position and do it again. If there is no match at all and the entire list is traversed through and there is no match at all, print search unsuccessful. So it's pretty straightforward. Go one by one, check against the key value. If it is found, yes, found. If not, say search unsuccessful. Let's look at a sample program and execute it, see how it comes out. Here is a sample program. As per the algorithm, I'm defining a linear search function with the list name that is being passed in the argument and the key to be found or the value I want to search in this particular list. for index in range 0 to length of the list. So for all the elements of the list, for every each and every element of the list, make a comparison against the key value. If the key is matching with the element at the current index position, then return the index plus 1 to get the physical position in the list. Else, return that key is not in the list. So I'm going to create an empty list, and the list is going to be filled with elements from the user input. So the user will be asked the question how many elements you want in your list. Once the user enters the number, the user is going to enter each and every element. So it goes through the range and keeps appending those elements into the list. So I end of it, say I want 5. I enter 5 as the number of elements. It will take 5 input elements, add it to the list. So I'm trying to print the current contents at the end of user input. And the next input from the user is expected to be the key that we need to search from the list. So enter the number to be searched, takes in, and find the position, assign the position value with the function output. So we have the index plus 1 being returned, right? If there is a match found, we are getting the index plus 1, otherwise none as the return. So index plus 1 will be the physical position. So position is assigned with the return value. If position is none, the number is not present in the list. Else, print the key is present at the particular position. So let's run it and see how it works. So here is the execution of the program. As per the program, it's asking for number of elements to be present in the list. Say I'm giving 6. So enter each element. I'm giving some random numbers. So it gives me the list in the order I entered. The complete list. The list contents are so and so. And it wants the number to be searched. I'm giving some number that is not present for now, right? Number 99 is not present in the list. I'm running it again. This time I'm giving the same 6 elements. I'm going with a new set of numbers. So it's asking what number you want to search. I'm saying that a number that is present in the list just to show how it works. Number 34 is present at position 3. Remember, this is the index plus 1. If you ask for if you printed the index value, it will be 2 0 1 2. But since we want the actual position in the list, we ask for index plus 1 to be printed, and it's printing 3 where the element 34 is present. We'll move on to the next method, binary search. Binary search, as we saw earlier, makes use of ordering of elements in a list to search a key faster than at least linear search. For numeric values, the elements are ordered either in ascending or descending. Text elements are ordered alphabetically, either A to Z or Z to A. The key to be searched is compared with the element in the middle of the sorted list. This is to either find a match or decide on what need to be searched in the second pass. That will cut down the size of elements to be searched in the next pass by half. The result can be one of three: a match, key greater than the middle element, or key lesser than the middle element. In case of a match, the search is considered success. In case the key is lesser than the middle element, then the half with large elements is ignored for next iteration. If greater, the half with smaller elements is ignored in the next iteration or pass. The process is continued until a match is found, else the search is considered unsuccessful. After all passes and we end up with 2 elements in the end and still there is no match, the search is considered unsuccessful. This process greatly reduces the iterations and in turn lesser time taken to sort. Let's look at the depiction of binary sort. I have a list that needs to be searched, some 9 elements, and I want the key 56 to be searched, or the number 56 to be searched, if it is present or not and where it is present, which position it is present from this particular list. So here is the process. So since there are 9 elements, Middle element is identified to be 39, and the value I want to search 56 is compared against 39. It's not present, and we have to remember it's an ordered list. In this case, we have the elements in the ascending order, and since 56 is greater than 39, naturally it's going to be present in the second half, or the half that has greater values than 39, right? So next iteration or next pass will completely ignore the elements 10, 12, 24, 29, and 39, because we are sure that the key that I want to search 56 is present in the second half. So the next pass goes through these four elements or the remaining elements, and the middle happens to be, since there are four and you cannot have a remainder when you divide by 2, it's going to pick the smaller of, or the left of middle elements. There are two middle elements and it takes the next left one and compares. Still it's not that, and it's going to compare against the next half, so it moves on to the next half, 56 and 69, and it identifies 56 at the index position 7, the physical position 8. So the key 56 is found at index 7, which is at a physical position 8. It's a simple depiction. Let's see how the algorithm is defined and a sample program. Here is the algorithm. I'm defining a function, binary search, with the list and the key to be searched. And I'm setting two variables, first and last. First to be 0 and last n minus 1. This is for the index values. Calculate mid, first plus last by 2. This is to find out the middle element. While first is less than or equal to last, step 4. Run the step 4. If the middle element matches with the key, then a match is found. So return element is found at position mid plus 1. This is the index position plus 1 at the mid, and stop the processing. Come out of the program. Else, if the key value is less than the mid position or the element at the mid position, which means the key is in the first half of the list less than the mid value. So set the last element in for the next search to be mid minus 1. Mid, of course, we have checked, right? Since it is not there in the mid, we are coming to this point. So we can ignore mid value also. So set the last element to be mid minus 1. So the next comparison, next pass will compare the key with elements from index 0 to index mid minus 1. Else, if the key is greater than the mid, it's not the mid values greater than the key here. Other, if it is the opposite, then set the first value to be mid plus 1, meaning in the next pass compare elements of the second half of the present list, or elements that are greater than the mid plus 1 value. Mid anyway is checked already, so go for mid plus 1. Even after doing all this, if there is no match, say print search unsuccessful. Let's look at a sample program and execute to see the results. Here is a sample program. I'm having a function with list and the value to be searched as arguments. I'm setting first and last values to have the index values properly handled. Print the number of elements. The last will be your number of elements. While first is less than or equal to last, meaning from left to right, or the first element to last element, find the mid value. If the element at the mid matches with my key, return the index mid. Else, if key is greater than element at the mid value, then set the first to be mid plus 1, meaning key is present in the second half of the current list, and the next pass will go from mid plus 1 till the end of the list. Else, if key is less than the element at the mid value, then my key is present in the first half of the list. So the next pass will go up to the mid minus 1, from 1 to mid minus 1. Else, if nothing happens, nothing is matching, then return minus 1. So to execute, I'm creating an template list, Create a list by entering elements in the ascending order. It's asking for elements to be in the ascending order. And end of each element press -99, because this is more of an aberration. It will not look into the ordered list. So this is just to end. Otherwise, you can have number of elements just like the previous linear search. You can ask for number of elements, enter so many elements in the ascending order or descending order, and then go for it. So input until you reach -999. Keep adding to the list, and before actually doing a search, print the first list or original list that we entered, and ask for the key to be searched. Call the function, and if position is not equal to -1, then the key is found at position, the index +1, else the key is not found in the list. Let's execute it and see the results. Here is the execution. Create a list by entering elements in ascending order. Please enter after each element. Press -999 to stop receiving inputs. So I'm going with the ascending order list and stopping with -999. So this is the data element I entered just in ascending order, and it's looking for a key to be searched. So I'm giving 90. I made a small change to the number of elements printing. It was given as last, whereas it should be length of B list. The last is your index position. So once I enter, it's going to give me the total number of elements to be 8, and 90 is found at position 6. I'm running it again just to show an unsuccessful search, a set of different numbers. And I want, say, 90 to be searched again. Total number of elements 7, but 90 is not found in the list. Coming back, let's look at the next search method, that is search by hashing. Hashing is a technique used to know the presence of a key in a list in just one step. How does it work? The basis for this is if the value at every index position is known already, then the search is much faster. Meaning, for every index position, what is the value present? If there is a way, or if there is a process which I can set the values or position the values as such, it will be easy for me to search a key value in the hashed table. Hashing makes search operations very efficient. Hash function takes elements of a list and generates an index for each value, resulting in a new list called hash table. Each index of a hash table can hold only one element, and the positions are indexed by integers starting with 0. So index values starting with 0 go in positive integers in ascending order, and each index of the hash table can hold only one element based on the hash function output. It's also called remainder method, a simple hash function that works on numeric values, takes an element from the list, divides by the size of the hash table. The remainder generated is called the hash value. The hash value of an element is element divided by the size. The percentage gives you the remainder, the size of the hash table. So let's look at hashing depiction. So here is an empty hash table. I just define a table for say n elements, n index positions. So each element having one index positions for to be referred. And currently there's no value. Now I'm trying to create hash values with hash function, applying divide by 10 on the elements 34, 16, 2, 93, 80, 77, and 51. So dividing by 10 with finding out remainder, 34 by 10 gives a remainder of 4, 16 by 10 gives a remainder of 6, and so on. 51 by 10 gives a remainder of 1. Now if I want to create a hash table based on this hash function application. So it could be a different device also, but the typical would be your size of the list. But in this case, for ease of understanding, it's done with 10. So I have the hash table that was empty before, and I want to fill with elements for each index. When each for in each index position, I want to fill a value of an element, right? So whichever is having 0 as the remainder will go into the index position 0, which is 80 as element here. So 80 goes into index position 0, 51 goes into index position 1, 2 goes into index position 2, and so on. So there is no reminders 5, 8, and 9, so they are not being filled, but the other ones are. So you might have a question here: what if there are two elements having same remainder values? There will be a contention. It's called collision. We will look at it at a later point. We have it as a discussion point. We'll look at it later. So here the hash table generated for the elements. After doing this, if I want to find out if a particular element is or key value is present or not, all I have to do is just go and find the index position and print the value. To search a key, calculate index use the hash function. So for example, I want to find 93. The hash function is divide by 10, finding the remainder, which is going to give you my 3 as the remainder. What is there at third position? If it is 93, yes, it's found out. Otherwise, the search is unsuccessful. Let's look at a program sample and see how it works. Here's a sample program. I'm defining a function hash find with key and the hash table as inputs. If hash table of key divided by 10 matches with the key, then key is present. So I return the key the index position plus 1 as the position, else return none. So as per the process, I'm creating a blank or empty hash table with all none as values. Print that as a blank. And I'm creating values of the element with a list, right? And print the list. For I in range 0 to length of the list, hash table, apply the function. This is basically the hash function, and assign that with the list value. Print hash table contents are, and what is there in the hash table after applying the function. Now for I in range 0 to the length of hash table, that is the length of the table, print hash index equal to I and value is the actual element value is present. Now, with this functionality of statements, I have the hash function applied and the hash table created for a set of elements, right? Now, if I want to find a particular element being present or not, receive that value from the user and find that against the hash table. Run the function with the key and the hash table as a parameter or arguments. If position returned as none, say we are returning either the key divided by 10, that's the remainder plus 1 as the position, or none as the position. So either return none or the key or the number is present at a particular position. Let's run it and see how it works. So here is the execution. I'm creating hash table for 10 positions with all none as values, and the list that is hard coded with the elements are 34, 16, 2, and so on till 51. And the hash table contents are at index position 0, I have value of 80, index position 1, I have value of 51, and so on. At the index position 9, I don't have any element. Now, what do you want to search? What element or what value you want to search? It's asking for it. So I'm saying, for example, 2. Number 2 is present at the third position in the hash table. 34, 16, 2. So it's basically your key divided by 10. That's the remainder plus 1 position. That is 3. And this is the physical position in the list. I'm running it again to show an unsuccessful search. So let's give 25, which is not present. 25 is not present in the hash table. So what will happen is, what the process will do is 25 divided by 10. You have 5 as the index value or the remainder value, but 5 there is none, so it's going to return 25 is not present in the hash table. I mentioned about a possibility of contention when there are two elements having same hash value or hash key value, right? So it's called collision. When each element of a list gets mapped to a unique position on hash table, hashing work perfectly fine. This is called perfect hash function. Whereas if there are two or more elements having same hash values, there's a conflict for position in the hash table. The reason being there can be only one element at an index position, right? So because of more than one element having same hash values, there's a conflict occurring. This conflict is called collision. Elements 26 and 31 in a list of 12, 26, 34, 31, and 57 will have a hash value of 1. When here we have 5 elements, and dividing by 5 will end up with 1 as the remainder for 26 and 31. And this particular conflict is also known as collision. Mechanism that places elements having same values in the hash table is called collision resolution. There are many ways of collision resolution, but we are not going to talk about them in this particular session. Few other hashing methods other than the remainder method are, the remainder method is also called modulo, when the percentage in Python parlance is called modulo, right? So it's either remainder method or modulo division method. But other than this, we have integer division, shift folding, boundary folding, mid square function, extraction, radix transformation. These are few other hashing methods. Each has its own implementation and algorithm, but they are not in the purview of this particular series. They take their own sessions, full sessions by themselves. The time taken by different hash functions may be different, but remains constant for a particular hash function. And we talked about so many methods, right? Each has its own time considerations. But if you take one hash method, it's going to be constant across implementations. The advantage of hashing is that the time required to compute the index value is independent of the number of items in the search list. So let's do a quick recap. Trying to locate an element in a list of elements is called searching. Linear search checks the element of a list one at a time without skipping any element. It goes or it covers every element present in the list to find a key's presence or not. Binary search takes a sorted or ordered list, divides it in the middle, checks for key value being present or not, and the key value being lesser or greater than the middle limit to reduce the number of iterations. Hash-based searching requires only one key comparison to discover the presence or absence of a key, provided every element is present at its designated positions decided by a hash function. When two elements map to the same slot in the hash table, it's called collision. The process of identifying a slot for the second and further items in the hash table in the event of a collision is called collision resolution. A perfect hash function maps every input key to a unique index in the hash table. In this case, there will be never a collision. Let's look at some sample programming hands-on exercises for you to try out. Write a Python program to search text using all three searching methods discussed, and try out a few by yourself. Search, you can imagine n number of ways, n number of applications or implementations. You can try out few by yourself. See you in the next session, where I can explain, or I'll explain some sample programs for all the exercises we have gone through from sessions 9 to 14. Thank you.